So one of the things I really enjoy about doing the online lectures is that I get to go back and see what I lectured about before, and I try to improve it, right? And so one of the things is I spent a fair amount of time just recently here uploading new information on the two presentations you're about to see here. And so with that, this is going to be historical geology and the history of geology. And then next, it's going to be the time scale, and so a history of the time scale as well. Now, gosh, what to tell you about it? There's a lot of names. I'm going to try to make it easier for you. If you think about this as like, what's the most important thing that person did? And so it's a lot of names, not so much the dates and everything, but know kind of what sequence things occurred in. And I guess I'll leave it at that. I'll give you the presentation, and then I'll give you a study guide later on about all the information that's going to be covered in this, and there's going to be a lot. So anyway, good luck with this. And so I really have a passion for history. I've got I don't have my pen here, but I've got a library behind me, and so I really like to read a lot, and so you'll learn a little bit on this one about kind of the history of the development of science, really, when it comes right down to it, the natural sciences. And so anyway, I'll talk to you soon. Thanks. Just a little explanation. The flag you keep seeing in these videos, that's kind of the pirate flag from a field trip back in 2008. We had a trip to Florida and visited the Keys and so forth. So here we are, the geologist with the hammer and so forth. That's our pirate flag anyway. So today's topic is historical geology and the history of geology. So we're going to move on. And what you see here in the foreground is the Delicate Arch. That is from Arches National Park, and that's near Moab, Utah, east central Utah. And behind that, you can actually see the LaSalle Mountains. Now, LaSalle Mountains were volcanic rock and an intrusive rock as well. And they kind of punched up through these sedimentary rocks. So they're actually an intrusive that's up about 12,000 feet in elevation. This is about 4,500, something like that, around Delicate Arch there. But anyway, it's a beautiful part of the world. And if you're in geology here at Missouri State University, we like to do field trips. And so we know that students learn best on field trips. And so we go to places like this, like the Four Corners trip. I think they visit Arches National Park. So when we talk about historical geology, first of all, we have to define what geology is. That's a study of the earth, of course. Physical geology, or principles of geology, we call it Missouri State University Geology 110, is the first course that you would take. And that tells you a little bit about earthquakes and volcanoes and plate tectonics. And you get to identify some of the various rocks. And then you learn a little bit about maps and so forth. And so we talk about water and all the things that you would expect to find in a Geology 110 book. But what you don't learn in there, in a textbook, what you don't learn in there is the history part of it. And so what is Earth's history? And so how did Earth evolve? Where did people come from? Where did the Earth come from? Where did the continents come from? And how did they assemble and break apart over the billions of years that is the Earth history? So the Earth is right now 4.56 billion years old, roughly. Although there's some discrepancy about the earliest age is 4.54, some people say. So anyway, that's this course. And so we're going to talk a little bit and expand upon what you learned in Geology 110. So you're going to have to know some of the things that you learned then. So we'll have a review after this, after we talk about the history of the time scale and so forth. But we're going to talk about the history of geology right now. So on to the next slide, you can see the Grand Canyon in Arizona here. And I want you to think about these strata as something like a book that's been flipped on its side, and the canyon cuts across that book. And it exposes different pages and different chapters and everything. And then sometimes those chapters or pages are pulled out. And so in this case, you've got Precambrian down at the bottom with an angular unconformity. And then above that, you get the Cambrian, of course. And so the Precambrian is, you can see a slight angle there. And so I try to point out with the arrow the base of the Cambrian there. And then above that, you get the Mississippian. Those are roughly the same age as the rocks around Springfield. And then above that, you get Pennsylvanian age rocks. Those are roughly the same age as the rocks around Kansas City. And then at the very top up there is the Permian, and those are roughly the same age as the rocks around Topeka, a little bit past Topeka, in fact, Salina, in that area in Kansas. So we get the same succession, but you have to drive miles and miles and miles to see all of these things exposed. In the foreground here, you see the same rocks, in fact. And so the red wall limestone's down here on this ridge that cuts across and juts across to the northwest, actually. It's to the left in your view of this slide. And then below that, of course, is the Cambrian. So the Cambrian is down there, that ledge at the very bottom on that ridge. So the Grand Canyon gives us an idea of what geologic history was in that location. We know when there was sediment going on, and we know when there was a hiatus, if you will, and so you form unconformities at those times. And so all of this record that we have, it's everywhere. You can get it with drilling and a bunch of other things, but it's a lot cheaper to go to a place where it's all exposed for you. So we call that the rock record, or sometimes we call it the stratigraphic record, but that is the history of Earth written in the rocks. And that's pretty important. So that's kind of like the impression that I want to leave with you to make sure that you understand it. And so how do we convey that information from one person or one generation to the next generation? Well, writing becomes really essential part of that. And so we learn about things and we write it down, and it makes our knowledge transferable. So in this image, you can actually see the Canoe Form writing script, if you will, from 3200 BC. They took a clay tablet and they used a reed in order to make marks that look something like a little trumpet. And so, the combination of different trumpet shapes together would indicate symbolically that that meant a certain word. And so a lot of this has not been translated, of course, but about 10% has. In Western culture, the Greeks came later, their civilization, and they had writing, they had language, of course, and they were able to discuss things philosophically in a dialectic. And so normally we regard the philosophers in ancient Greek society as either pre-Socratic or from Socrates onward. And so all of these are, Thales would be pre-Socratic. And he thought that the earth was kind of hollow and with a hardened crust on the outside, and that it was filled with ocean water. And so wherever there's a break, the oceans would spill out, essentially. Other ideas about the earth. Anaximander recognized fossils. It was Aristotle, however, who suggested that these fossils are probably from spontaneous generation. They could grow right in the rock. And that's an idea that would stick with both the Greeks and then also later with Christian cultures of the all the way into the Middle Ages, that you could actually spontaneously, God could have caused things to grow directly in the rock. Xenophanes of Colophon found fossil fish, and he reasoned that rock and water were interchangeable. Same sort of idea. So you could change water into rock, essentially. But, these were fossils. But what were fossils, And there was nothing to tell these folks what anything was. And so they had to reason out all of this sort of information that they're really essentially surrounded by in the natural sciences. So it was Pyrrho at the very end there. He became important in science because he's the first one who introduced the concept of skepticism. It's like, show me your evidence, and maybe I'll believe you. So fossils have always been this enigma. And so here's a couple of varieties right here. So the ammonites on the upper left here, that's named after the god Ammon from the ancient Greeks. He was the ram god, if you will. And on the right-hand side are, you can tell what they are immediately, right? You say they're shark teeth, but nobody knew what they were back even in the Middle Ages. That became controversial, in fact. So a lot of the folks at the time thought that these things would actually form spontaneously, plastically within the rock, or have been formed during creation at some point. And then, so even if you have materials like this that are pretty obviously bony and enamel covered and so forth, and the ones from Malta were actually referred to as glossoptery, and the glossoptery or glossoptera, single one, meant tongue tooth, or tongue rock. So Petra means rock, of course, and Petri means multiple rock, I guess you could say, but gloss meant tongue. And so with it's always been a puzzle. Where do these things come from? And so most people, of course, thought that the earth was pretty short in duration. Now, the ancient Greeks, to their credit, thought that the earth never had a beginning and will never have an end. We know that that's incorrect, but then again, when you get into later cultures, the Christian culture from the very inception of it, took a literal rendering of the scriptures, and they said, if you count the years that are listed in here, there's roughly 6,000-year-old Earth. And so that's where some folks are still stuck today. So with these fossils, remember also this, like, you could make a writing, but it had to be done by hand, right? And usually it was learned people, but most of those learned people were also in the church all the way into the Middle Ages. And so it was an argument. There's actually a group of really smart philosophers would sit around and it's like, well, I don't believe that. I don't believe this. It's like there began this sort of like push towards the scientists to sciences back in the 1600s. But even they argued that the roots of it actually came from better navigational skills, which came around with the compass. So the compass is one of these sort of devices by which you could actually navigate the oceans of the earth. And the sailing ships had increased dramatically. No longer were they stuck on the Mediterranean, but they could go the entire world, all the way when they got into the 1400s, of course. And so by 1450, the printing press had been invented. And all of a sudden, it was easier and less expensive to transfer knowledge from one place to another. And by the 1600s, there were guns that were available, right? So this idea of gunpowder made its way into European culture as well. And so the matchlocks and the muskets of that time became a way to overthrow the existing power, if you will. And so war actually became more common in the 1600s. And at that time also, of course, there was the development of the Protestant Reformation at that time. And so the church had a split then as well. So in the 1600s, there was philosophical, do we stick with these old ways with the church, or do we go to this new pathway, or do we form our own nation, and so forth, and overthrow the kings and so forth. So the first king, I think, that was ever pretty much overthrown and taken over by a popular government would have been in Britain. And that would have been Cromwell. But it's ironic, but actually the Restoration, that is when a Catholic king was put back in charge of Britain, that's when they developed their science, actually. And so that was the reign or the rule of Charles II. And so they formed a society called the Royal Society. And it was kind of founded on something called the Invisible College. And the Invisible College were these gentlemen who were the philosophers of that time. And they would sit around and present new information. They would study things. 1635, the French also had the same sort of like pathway forward. And that was actually through the church as well. And that was Cardinal Richelieu. And that's the Academy of France. And so there was this appreciation of skepticism finally during this age of enlightenment. So what you see down here at the bottom is Cardinal Richelieu. Then you can see Bacon is the second one. So he kind of just predates the formation. His life predated the formation of the Royal Society. He would have been part of that Invisible College, however. The next person is Boyle, Robert Boyle, who was responsible for Boyle's Law and gases and so forth. And then lastly, there's Newton, who was an absolute genius and spoke about many things, but he also, discovered the calculus, and he understood gravity for the first time, the relationship between gravitational pull of the Earth and objects. So it explained gravity anyway. So that was the beginning of science right there. And so into this sort of like setting, and a little bit earlier even, in fact, in the 1630s, this gentleman was born, Niels Steensen, or he became known as Niklas Stenonas. We call him Steno in geology, so it's just shorten the whole thing up because it's spelled very many different ways. But he was born in Denmark in the middle of the 30 Years' War between the Protestant Scandinavian countries and the Catholic German Federation. And so he was born into that, and there was the war was going on around him, essentially. And so as a young man, he went to the university. His father was a watchmaker, and at the university, he became very skilled because of his practice of helping his father with the watches and so forth in dissection. And so he was actually an anatomist. He studied medicine, in other words. And so, but despite the fact that he studied medicine and put on exhibitions, and he's like, okay, I'm going to dissect this eye. And he discovered several different organs and so forth. Like there's a steno, sort of like steno sort of organ associated with, I think it's the salivary glands or something like that. He discovered that. But he went on and he would do demonstrations in places like Amsterdam and so forth. But when he finally went to Florence in Italy and actually became part of the Medici court, he had the opportunity to study a lot. And so he was a paid scientist, essentially working for this academy, and that academy was called the Ciamento. And there were a lot of other scientists that he could discuss his ideas with, and he would go out in the countryside and examine things. And so it was Steno who eventually wrote a short tract, actually, and it was called De Solido Intra Solid Naturaliter Contento. And so he gave us in that book some of his ideas about superposition, about original horizontality, about lateral continuity, and then also cross-cutting relationships in rocks. And he also made speculations about those Glossoptera or the Glossopteri from the island of Malta. And he says, I think that these things were alive at one time. And that all came about because there were some fishermen along the coast of Italy here, right? And so he's in Florence, and along the coast they caught a shark, and they cut the head off of that shark. Now that's very uncommon to catch a shark back in those days. Everything was netted fishing, and so they caught this shark. They killed the shark. The shark was beheaded, taken to this great anatomist, and he began to dissect it and everything. And so there's an illustration I have on the next slide here. It shows you, he dedicates this to Ferdinand Medici, and Lorenzo Medici was his brother, right? And so there's this huge flourishing of science in Florence at this time. And so there's the shark illustrated over on the right-hand side, and some of the shark teeth that resemble some of the Glossopteri that you've already seen. So he did all of that and more. So in fact, in many ways, he's the father of geology. Now, I don't claim that he's the father of geology, and most people wouldn't claim that either, although some people do. But these very core ideas that were established became part of the geologic understanding that was later applied over the next 2 centuries so that people could figure out this puzzle. So superpositions, this idea that in any sequence of undisturbed strata, in other words, they're not folded, they're not uplifted and faulted all to heck and so forth, right? The oldest strata is always going to be at the bottom, because you got to have something at the bottom and then you pile things on top of it, right? A very simple concept, but it's called superposition. A lot of people forget this, or they confuse it with original horizontality. Now, we talked a little bit about original horizontality already, but not a lot. We're going to talk about it some more today. With original horizontality, we're saying that sediment originally is generally deposited in flat layers. And so whenever we see layers that are upright and so forth, or have some sort of inclination, very commonly those are ones that have been moved that way by some sort of tectonic process or some sort of natural process that would cause them to become dipping strata, if you will. And so that is original horizontality, is that idea, superposition, just that you stack younger on top of older. And lateral continuity says that if you see something on one side of a canyon, you may expect to see it on the other side of the canyon, that it probably was continuous across there then. And so that's how people can make assumptions about, if you see this set of rocks here, if we go over one county, are we going to see the same set of rocks? Well, you may or may not, because it was Steno who said that rocks are going to be deposited in a relatively flat area, and they will continue on until they reach a barrier of some sort or they peter out. In other words, they are going to maybe pinch out, or they will come up against some obstruction. And so that's this principle of lateral continuity. And then lastly, he reasoned in that if you have something that cuts something else, then it must be younger than whatever the material is that's cut. And so that was later expanded upon by James Hutton and also by Charles Lyell. We'll talk about them in a little bit here. But anyway, cross-cutting relationships is generally attributed to then Steno as well. Those are the four major ones right here, but also his ideas about fossils as well. And so we're going to revisit fossils in here as well. So what is superposition from an original horizontality when we look at images? Obviously, in the upper left-hand side, that's Canadian Rockies, and it's one of the places where you might expect to find layered rocks in the mountains here, and they go right up the hill. They're slightly deformed. You can see there's a slight syncline in the middle of that upper cliff on that mountain, but and they're very steeply dipping, right? But they originally would have been horizontal and pushed into that sort of like position that they're in right now. On the right, upper right-hand side, you can see that's called Dome Canyon there, and this is right off an offshoot off of Margam Canyon in western Utah. And these are relatively flat-lying strata of limestone here, and you can see the canyon cuts up and exposes the face of these rocks here. But those things would have continued on to the west farther. That's an east-facing dip on those rocks there, and a north-facing, trending dip on the rocks that are at the very bottom of the lower left-hand side here, and that's Steamboat Mountain, also in the House Range in western Utah. And original horizontality here, easy enough to figure out. These rocks have just been slightly tilted then, right? And superposition, well, okay, so then the older rocks are going to be at the bottom and the younger rocks at the top. In fact, right in that succession here that you see, you're looking at the boundary between what most people regard as Middle Cambrian time and Late Cambrian time. So it's up in the middle part of that slope, essentially there. On the lower right, you can see some rocks that are exposed near Branson. And those rocks, in fact, include both lower Ordovician age rocks in the lower part, and then Mississippian age rocks towards the top there. And so those are lower Carboniferous. And the boundary between them is roughly where, let's see if I get it right here. It's about, you see the orangish layer that's on the left-hand side. It's going to be tough if you're colorblind maybe, but there's a shelf and then another shelf, and then the third shelf at the top of that stack of rocks, if you will, is roughly where the Mississippian begins, and below that's lower Ordovician age rocks. So it's pretty obvious from that, right, that they've just tried to fill in what is a fracture that's been solution enhanced, and it's really, there's a cave at the top of that up there. And so they ran into a lot of caves when they were putting the highways in around Branson. And so they've tried to fill in, but it's easy to tell what's man-made and what is not in that situation. So when we talk about strata, we're talking about natural sort of phenomena as well. Okay, so if we go on to the next slide, you can see in this photograph, that's mostly chert. Actually, it's a rock material called Novaculite. It's a lot like chert and shale. And those rocks are slightly folded, and then also they're probably faulted a little bit. I think there's a fault that runs up pretty close to the left-hand side there, where it runs up in the western, in the left-hand third of the image there. But then also these rocks would have been deposited in a relatively flat sort of setting in an ocean basin. And so the original horizontality, you have to rotate these rocks back to their original position, in other words. And mountain building processes brought them to this sort of like orientation now, or they're vertical. If you go to the next slide, here's another setting. This is in Missouri. And the last one, by the way, is from the Ouachita Mountains in west central Arkansas. The photograph that you see here is the Decaturville structure, just a little bit north of Lebanon, Missouri, and you can see the rocks here are all dipping. They would have originally been relatively flat, but now there's even a fold in this right over, that's Nancy walking down the highway there, and so I'm taking a photograph with her, and she's actually being the scale for this photo. There's actually an anticline right there just above her here, and you can see that the rocks farther back are dipping away, and then the rocks on her side of that fold are dipping towards her. So that's an anticline. And the rocks are generally dipping to the south here on Highway 5. So, but they would have been originally flat. And they were brought to this sort of like orientation by some process, right? In this case, it's not orogenesis, it's not the building of mountains. It's from a meteorite impact, which happened a little bit to the left on this image. Fascinating sort of place, right? So if you have, we talk about original horizontality. Does that mean there can be no irregularities on that surface? No, it doesn't mean that, because in this case, that's a natural sort of irregularity that you get in relatively flat strata. Those are called ripples, right? And those are what we refer to as primary sedimentary structures. And so sedimentary structures can be on relatively flat sort of rocks, and you get that sort of like preservation of these ripples if you cover them perhaps with shale. And so they're very nicely decorated. This is at Bennett Springs Park. If you go across the bridge there, you'll see these ripples. In this slide, you can actually see the Burlington limestone, and it's been folded and then also thrust faulted slightly. The guy in the image here, he did work for an oil company. I don't know if he still is, Brandon Zates. And so Brandon is kayaking. We did a kayak trip on Truman Reservoir, and this is up around Osceola, Missouri. And at the base of the Burlington limestone here, it's been faulted and also it's been folded. And the fold itself is actually broken. And so in that fold, what could cause that? Originally were deposited horizontally, obviously. But in this case, again, deformed by another meteorite impact. We got 3 of them in Missouri. So that impact actually shunted these rocks up to the north and west in this locality. And so that has yet to be worked on, the structural geology of that impact. So on to the next slide. And you see here, this is kind of a trick question, actually. What's the original horizontality here? You can see some of the beds in here appear to be horizontal, but then you get these laminae that are dipping off to the right. And some of them are kind of curved a little bit and so forth. But you can look at these things as though they are sets of laminae, and those sets actually are relatively flat. And so there's a set of laminae that are kind of gently curved and trending off to the right-hand side, and then the next ones do the same thing, and then the next ones head the same direction. And then there's at least like 5 sets that are exposed in this photograph. And these things are called crossbeds. And so crossbedding is a process by which you can march sediments across the surface and have that surface not actually horizontal, but it's the actual slip surface of where those sediments would have built up and then maybe avalanched. And so it's like a sand dune. In fact, if you cut into a sand dune, you're going to see similar crossbedding like this. And in fact, that's the composition of these rocks. That's a quartz sand. And of course, they're crossbedded. So in the next image, you can see the same process, and they're interbedded with shales in this case, and that's in eastern Kansas right here. And those are sandstones again, and the shales are the darker layers in there. And you can see that they're slightly dipping towards the left in that photograph, all through just above the hammer there. They're dipping off to the left, and that's crossbedding. And crossbedding, what we say, so in other words, we're not holding up a strict, question is like, is this horizontally bedded? It's like, well, no, it has some depositional dip to it. Does that mean that it violates this principle of original horizontality? No, not in the slightest, because if you take it in a more thicker succession like this, those are relatively flat. They've not been deformed through orogenic processes. So that is another situation where you have cross-bedding here. Now the next one, it takes seismic to be able to show this. And so this is from the North Slope of Alaska. I used to work at the USGS, as you know. And so one of the targets that folks look for out there is the Nunukshuk sand at the very top up there. Is about 30-foot thick sand that has millions of barrels of oil in it. And so when they're looking for that, they always see these sort of like, it looks like dipping strata below that. Now this has been interpreted, right? So there's a record that gets collected first. And then in this case, they've drilled through those rocks to find out what was there. And they can show you where they drilled with that vertical line. And then they ran a log through it as well. And so they have the electronic response with, it's called GR, that's a gamma ray. And it goes from 0 to 220 up there. That's a scale on the thing. And so you can see that it gets hotter on the right-hand side. That means there's more organic material usually in it. So with that well, they penetrated through what's known as the Torok. And so the Torok is the name of that rock unit that has all those dipping laminae in there. And they're not laminae in this situation. They're actually bed sets. And so there are thick beds in there. And there may be some slumps and things like that in there as well. But that was a time when there were the edge of Alaska, if you will, had already collided with the rest of North America, the upper part of Alaska and the Brooks Range. And so it built out a shelf, a continental shelf, and that's what you're seeing the result of there in the Torok clinoforms. And so they're a large-scale equivalent of cross-bedding. And so the clinoform itself is actually the dipping surface in that, and so it's pretty neat. And so when you look or explore for oil and gas, you interpret different sorts of data, but the same processes apply. Well, does that violate the principle of original horizontality? Well, if you look at the black line that marks the top and the black line that marks the bottom there, those are unconformities. That's in fact, those are an unconformity at the bottom there is called the Lower Cretaceous unconformity. It's a regional unconformity out there and noted for its organic content. And so a lot of oil and gas in the North Slope of Alaska. And so, no, I mean, if you take it in a gross scale, it doesn't violate it at all. And so you're looking at something that's on the order of 2.7 kilometers or 1.7 kilometers in thickness. And yet, overall, it's relatively flat. It's not been deformed by mountain building processes after that. Okay, now the next one. This one's kind of interesting here. You've got a Precambrian quartzite stuck on the top of a Cretaceous shale. And so hopefully you're already studying some of the geologic timescale, and immediately this should raise some red flags, and you're going to say, oh, but the Cretaceous is like at the end of the Mesozoic, and that's Precambrian up there. What's that doing on top of, upper Mesozoic age rocks? That's Chief Mountain in Montana. Now, you know that the Rocky Mountains were deformed, okay? We talked about that a little bit with Dinosaur, well, we haven't got to Dinosaur Ridge, but anyway, here you have, well, we did, didn't we? Yeah, we talked about Dinosaur Ridge. Anyway, here is Chief Mountain. How did it get on top of those rocks? Well, it's a special type of fault. And in fact, they call it the Lewis overthrust, and that's right at the base of the cliff there. And so those Cretaceous shales that are down there are kind of slippery. And so when you push these rocks, we're talking about collisions of microcontinents and things like that, and it pushes these rocks, piling them up on one another, and so sometimes they slide. And so Chief Mountain was actually what it was a result of a sliding essentially across the top of that Cretaceous shale there. Now, of course, it's been weathered, and much of the Precambrian quartzite's been removed, but hasn't been that long ago. In fact, maybe tens of millions of years ago that was in place right there. So that is an example where it actually violates the law of superposition in this case. It actually does violate that, and that's because of a fault relationship. And so that's an interesting situation. In the next slide, you actually can see here one of the earliest cross sections that was ever made by John Strachey And he was a mining engineer, and he was interested in finding coal beds, of course. And so you see an intrusion that cuts those coal beds here, and the coal beds themselves are dipping. This is in the north of Britain, and they're dipping off to the east here. And you can see there's a set of 3 on the right-hand side and a set of 3 on the left-hand side there. And so that intrusion actually must have followed a fault in that it offset those. And so the right-hand side was uplifted relative to the left-hand side. In the parlance of describing this fault, you would say that probably is the hanging wall on the right-hand side, and the footwall would be on the left-hand side then. John Strachey knew nothing about that at this time. He didn't even know what age these things were, but he was interested in finding the coal. And because they had a few coal mines that were established across here, he was able to show that there's an unconformity at the very top up there. You can see the flat lying strata at the very top. That's an angular unconformity. And then below that, these dipping strata, and those dipping strata, in fact, he didn't know why they were dipping. And he thought perhaps that during the Great Flood, there would have been like a whirlpool in this area that caused these beds to dip. Today, we know that's not a valid sort of explanation for these rocks. On to the next guy here. And so we've examined Steno, and we've talked about John Strachey slightly. So this is our third individual to talk about here. And his name was Arduino. And Giovanni Arduino lived and worked in the northern part of Italy in the Alps, close to Vicenza. And then he's the first guy to identify that there are different ages to these mountains as well. He saw rocks that were made out of crystalline, mountains that were made out of crystalline rock. And then he saw some that were made out of layered rock, and he called those the primary. Well, the primary ones were the crystalline rock, and then the secondary rocks were composed of sedimentary strata, fossils in them even, in fact. And so he recognized the fossils as well. And this is a time when people were just beginning to understand what fossils were. They really didn't have a good grasp on it yet. And then lastly, there are these tertiary mountains, which were composed of sand, gravel, and clay. And that would have been on the north side of the Po River in the north of Italy. He developed this idea that you can actually do relative age dating just on the type of mountains that are there. And so Arduino is one of the pioneers. He's an Italian pioneer in understanding geology. In the next slide here, you can actually see one of his illustrations, and he shows these different rock layers and illustrates and then made notes down below about what type of rock he found there. And so people began to identify rocks at this time and to be able to see that they belong to different sort of like time periods, if you will. So he had the primary, secondary, and tertiary there. And so that's pretty important because one of those words is actually had stayed with geology for hundreds of years, and it's only recently been retired, and that's the word tertiary. We don't use the terms primary and secondary anymore, but we still had used the word tertiary, and we still use it, in fact, in places like on geologic maps and so forth. Okay, next on this is somebody came along and relooked at some of his work. And you can actually see a modern illustration of that duplicates his notes. And so you can kind of see the thought processes that went into his developing his understanding of primary, secondary, and tertiary rocks. In the next slide, you can actually see the geologic map for the area that he was studying. It's very close to Venice. You can see Venice on the right about in the center of that slide in the north end of the Adriatic Sea there. But that is the lagoon that surrounds Venice there, and then the Po River is at the in the lower half or the lower third of the image here. But the rocks are then exposed up in the mountains here, and so this is a geologic map that was made much later, of course. But in the next slide, you can actually see the area where he studied. So those are some of the mountains and the mountain valleys that were up in the Alps that Arduino studied. Next, we go to another Italian, Anton Lazzaro Moro. He was born in the same area, not in the same province, but a little bit farther to the east from where Arduino was. And he was another gentleman who was an abbot actually. So he was in the Catholic Church, but he also studied geology. And so he was a naturalist, and he recognized in that vicinity that he was dealing with a lot of, igneous rocks. If you're in Italy, one of the more natural things that people do is to go see, and everybody's heard about Mount Vesuvius, of course, volcanic in origin, right? And then if you go to Mount Etna on Sicily, you've seen those are more volcanoes, right? And so he found the same thing in the Alps as well. And so he also recognized this idea of primary and secondary rocks. But then he also saw that there were some sedimentary rocks. And so he thought that most of the rocks probably came from volcanism. And then next you have, and in fact, so if we back up here, Lazzaro, Anton Lazzaro Moro, was a founder of a school called Plutonism. Plutonism is Pluto is the god of fire, I guess, in the Greek realm, as opposed to Vulcan. So Plutonism is this idea that rocks were formed from fire. Now, this is inherited from the Greek philosophers. They recognize there's earth, wind, fire, and ether, right? And so earth, wind, fire, and the air around us. And those four elements pretty much confined everything. And they tried to explain everything within the concept of those four elements. And they didn't have 92 elements, that we have today to think about because they hadn't been discovered yet. And so he came up with this idea that everything was fire made. And so if you're going to have sediments, they're going to be reduced from what was a volcanic rock at some point. In contrast to that, Abraham Gottlieb Werner from Germany, he was the founder, and he said that no, the rocks come from the water. And so he named this the Neptunism theory about the origin of rocks, and even rocks like a basalt he ascribed to forming inside or from water itself. And so Werner had that idea, and so he founded the school that became known as the Neptunists. Of course, Neptune, the god of the sea, with the trident and so forth. And so these primary rocks, these primitive rocks, crystallized out of the sea. And he didn't really have a good explanation for the fossils, right? But alluvium covered those rocks, so he called them primitive, transitional, and then alluvium is the very top part here. Okay, so now you have on your list of notable people to remember, you have Steno, you have Arduino, you have Moro, you have Werner, and now we're getting to probably one of the most important people and influential in the history of geology, and that's James Hutton. He's at the upper left-hand side here. Just below him is his good friend John Playfair. Now, these guys were Scots. Hutton grew up in the south of Scotland, in the lowlands, and Playfair, there's actually a monument to him in the capital city of Edinburgh. It was Hutton who actually, even though he was a Plutonist and thought that all rocks probably originated from fire, he's the one that gave us the concept of deep time. He said there's no vestige of a beginning and no prospect of an end. And that's kind of like the Greek philosophers thought. And he also gave us this idea of actualism. Actualism is what we see. In order to explain it, we don't have to call upon supernatural processes. And so the present is the key to the past. And so he said things happen incrementally in slow periods of time. And so they call that uniformitarianism. And that was a prevailing thought in geology all the way up until the 1980s, I would say, maybe 1970s. There's a few different situations where you can actually call upon a different sort of origin for the processes that operate on the Earth. But it was Hutton who gave us this idea of deep time and uniformitarianism. So Playfair took Hutton's work and publicized it, actually. So he was kind of like a ghostwriter, if you will. And so he actually wrote the book that was much more popular than Hutton's own writings. Hutton's writings were pretty impenetrable trying to read them. But Playfair made them readable and accessible for the common reader. So what did Hutton propose? Okay, so a little story. Hutton, coming from an area in the south of Scotland, had a farm. He had a farm called Slee Houses, and Slee Houses was across or very near Roman ruins, and then also some medieval ruins of castles and so forth, right, that had fallen into decay. And he recognized that when you look at those two sets of ruins, one of them was much more weathered than what the other one was. And he said, erosion must be very important. And he looked across his fields and he saw rivulets that were cut across, small streams that were cutting across his fields. And it's like that sediment, when it rains, that sediment gets washed away. Where does it go? Well, it follows that creek down to the river. And then the river, where does it go? Well, it goes down to the sea. And he saw for the first time this connection between rock and then the weathering and erosion of it, and then the transportation of it to a depositional basin. And he says, oh, I see it now. So you can actually uplift these rocks, form the sediments, piles of sediment, if you will, and then erode them and deposit them somewhere else. Roughly, he came up with like 2/3 of the rock cycle as we know it. And so these uplifts occurred to bring intrusives and the overlying rocks closer to the surface. The sediments that these formed were from deeply weathered rocks that eventually were buried in the oceans, perhaps, and they turned to sedimentary rocks. So, in fact, the Earth must be incredibly old. So we're going to look a little bit at the evidence for his understanding of this. And so I'm going to actually stop the presentation right here, and we'll pick it up again with the evidence for Hutton's understanding of Earth. So I'll talk to you in just a bit here.